In the previous few lectures, we discussed symmetric key cryptography. We now start our discussion of public key cryptography. So the motivation for using public key cryptography is the following. Recall that if a sender Alice and a receiver Bob use symmetric key cryptography, then they must first agree on a common secret KS, which is the symmetric key used for encryption and decryption. For example, in the case of Caesar cipher, the symmetric key is the shift value used by used for encryption and decryption. And in the case of a block cipher, the symmetric key is the one-to-one mapping used to map the plain text to the ciphertext. So before a sender and receiver use symmetric key cryptography, they must agree on a common secret KS. The question is, how can the sender and receiver agree on a common secret KS? So in some context, this can be easily done. For example, suppose a bank and a customer want to securely exchange messages over a network such as the internet. Then the bank can first send the secret key KS to the customer by post. This is possible because the sender and receiver have access to a communication channel other than the insecure channel over which they will be communicating. So they have this is called an out-of-band channel. So when an out-of-band channel is available, it's easy to agree on a secret symmetric key. But suppose that the only way that Alice and Bob can possibly communicate is over a network, and the network has the property that any message that is sent over the network can be sniffed by intruders. In this case, is it possible for Alice and Bob to communicate securely? The answer is not very obvious. How can Alice and Bob agree on a secret symmetric key KS when all the messages they exchange can be sniffed by intruders? In the 1970s, it was shown by Diffie and Hellman that the answer to this question is yes, it is indeed possible for Alice and Bob to communicate securely. So this was a major breakthrough in cryptography. The reason is that for a long time, that is from the time of the Caesar cipher to Diffie and Hellman's discovery, encrypted communication required that the sender and receiver share a common secret KS in advance, and this was done manually. For example, via the dispatch of trusted couriers carrying locked suitcases wherein the key was stored. So sharing the secret key KS in advance was time consuming and expensive. After the invention of public key cryptography in the 1970s by Diffie and Hellman, the sharing of a secret symmetric key KS became much easier. Suppose Alice and Bob do not have a shared secret key in advance. Alice wants to encrypt and send a message M to Bob. Bob has two keys. One is a public key, let's denote it by KB plus, that is available to everyone. For example, it may be included in a database similar to a telephone directory. And the other key that Bob has is a private key KB minus that is only known to Bob. So care must be taken to ensure that the private key KB plus does not leak and it is not known to others. The private key KB minus must be known only to the receiver Bob. The public key KB plus, in contrast, can be known to everyone. In fact, it is required for others. For others to be able to send encrypted messages to Bob. This shows the scheme used for encryption using public key cryptography. Suppose Alice wants to send an encrypted message to Bob. Alice first fetches Bob's public key KB plus, possibly from a database such as a telephone directory. So that's shown here. Alice fetches the public key of Bob KB plus, and then Alice computes the encrypted message KB plus of M, where M is the plaintext message and KB plus of M denotes the plaintext message encrypted using Bob's public key. So to compute this message KB plus of M, Alice uses the public key KB plus and a known encryption algorithm, possibly a standardized one, and then Alice sends the message to Bob. These are the steps. First, to send a message from Alice to Bob, first Alice has to obtain Bob's public key and then encrypt the plaintext message M using Bob's public key. KB plus of M is the ciphertext obtained, and then Alice sends KB plus of M to Bob. Now Bob receives KB plus of m and then uses his private key to compute KB minus of KB plus of m, and that is equal to m. This computation is done using a known decryption algorithm. So notice that the public key and the private key are related because if we take a plain text message m and then first encrypt it using the public key KB plus and the encryption algorithm, and then take the result and decrypt it using the decryption algorithm and the decryption key, that is the private key, in that case we get back the original message m. So KB plus and KB minus are related. But the selection of KB plus and KB minus must be done carefully, as we'll see. We study algorithms for selecting the public key KB plus and the private key KB minus and the encryption and decryption algorithms such that this property is indeed true. First encrypting using the public key and then decrypting using the private key yields the original message m. So note that KB plus is known to everyone. It's stored in a database such as a telephone directory, and KB plus and KB minus must be such that it is impossible or computationally infeasible to find KB minus using KB plus. So the catch is that KB plus and KB minus are related. They are related. It is apparent that they are related from this relation here. So KB minus of KB plus of m equal to m. So clearly KB plus and KB minus are related. But still, using the knowledge of KB plus, it must be computationally infeasible to find KB minus. So we require a clever algorithm to select the public key KB plus and the private key KB minus. We study the RSA algorithm. It is a widely used public key cryptography algorithm. It is named after its inventors, Ron Rivest, Adi Shamir, and Leonard Edelman. So hence the abbreviation RSA after the inventors. So the basic idea in RSA is the following. P and Q are two large prime numbers. They are known only to the receiver, Bob. His private key is found using these prime numbers P and Q. So Bob knows P and Bob knows Q. So Bob individually knows P and Q, whereas n equals PQ, that is the product of P and Q, is known to everyone. It is a part of the public key. The security of RSA is based on the fact that there are no known efficient algorithms for factoring a number n into its prime factors P and Q. So the most efficient way known is to essentially try out all the numbers less than root n. Clearly, since n equals P times Q, one of the factors must be less than or equal to root n. So clearly it is enough to try out numbers up to root n. So once we get one factor, then we get the other factor automatically. But the problem is that for factoring n, there is no known efficient algorithm. The only way known is brute force, that is trying out all the numbers less than or equal to root n. We don't know any algorithms that are more efficient than much more efficient than brute force. So if n is large enough, then it is computationally infeasible to find the private key using the public key. For example, n might be, say, 1024 bits. N might require 1024 bits to represent. So in this case, it's an extremely large number. In this case, it's difficult to computationally infeasible to factor it out into its prime factors P and Q. So recall modulo n arithmetic, which we reviewed in the mathematical background for cryptography. RSA makes extensive use of modulo n arithmetic. Recall that x mod n denotes the remainder when x is divided by n. For example, 19 mod 5 is 4. We have these properties which we discussed earlier. A mod n plus b mod n, the whole mod n equals a plus b mod n, and we have similar properties for subtraction and multiplication. We'll use these properties in the sequel. Suppose Alice wants to send a message m, which is a bit string, to Bob. Now any bit string can be equivalently represented by a positive integer. For example, the bit string 1001 can be represented by 9. Notice that the binary representation of 9 is 1001. So in RSA, we represent the original plaintext message by some positive integer. So the components of RSA are the following. One component is the choice of the public key and the private key, and the other component is the encryption and decryption algorithms. So we'll discuss each of these components in detail. First, we'll discuss how to choose the public key and the private key. Then we'll discuss what are the encryption and decryption algorithms. So here is the algorithm for generating the public and private keys. We choose two large prime numbers p and q. The trade-off is that larger the values of p and q, more difficult it is to break RSA. But on the other hand, encryption and decryption times start increasing in p and q. So larger the values of p and q, more difficult it is to break RSA, but the encryption and decryption times are larger. So p and q must be selected taking into account this trade-off. Now let n be the product of p and q and z be the product of p minus 1 and q minus 1. For example, if p equals 5 and q equals 7, notice that p and q are prime numbers. In this case, n is the product of p and q, that is 35, and z is the product of p minus 1 and q minus 1, that is 4 times 6, that is 24. So these are very small numbers. In practice, p and q are obviously much larger. Next, we choose a number e less than n such that e and z are relatively prime. Later, we'll see the reason for the fact that e and z have to be relatively prime. In this example, e might be 5. So notice that 5 and 24 are relatively prime. Next, we choose a number d such that e d mod z is 1. Later, we'll show that a number d always exists when e and z are relatively prime. A number d such that e d mod z is 1 always exists when e and z are relatively prime. So in this example, d might be 29. So notice that 5 times 29 is 145, and 145 mod 24 is 1. So d is such that e d mod z is 1. Now the public key kb plus is the pair n comma e, and the private key kb minus is the pair n comma d. So this is the algorithm for selecting the public and private key. So the public key is the pair n comma e, and the private key kb minus is the pair n comma d. Now let's discuss how to perform encryption and decryption. Suppose Alice wants to send a message m, which is a positive integer, to Bob. So m must be less than n. If the original plaintext message is large, then we can always break it into chunks such that each chunk satisfies the property that m is less than n. Now the encrypted value c is calculated by Alice as follows. C is m to the power e mod n. C is sent to Bob. Now at the other end, Bob performs decryption as follows. Bob computes c to the power d mod n, and the claim is that c to the power d mod n is equal to m, which is the original plaintext message. So notice that for encryption, Alice used the public key of Bob, that is n comma e, and for decryption, Bob used Bob's private key, that is n comma d. So these are the steps for encryption and decryption. This is an example which illustrates the operation of RSA. Originally there are 4 plaintext messages. These are 12, 15, 22, and 5. These are encrypted and sent by Alice. So m to the power e is this. This column provides the value of m to the power e, where e is 5. And then this value provides, this column provides m to the power e mod n. So these are the ciphertext messages corresponding to these plaintext messages. Now these ciphertext messages are sent over the channel by Alice to Bob. Now Bob takes these ciphertext messages and performs c to the power d mod n. So c to the power d is shown in this column here, and then c to the power d mod n is shown in this column. So notice that Bob recovers the same plaintext messages that were sent by Alice. So performing encryption first and then decryption recovers the original plaintext. Another key observation is that even for this small example where n is just 35 and e is 5 and d is 29, even in this example with small values of p and q, notice that these numbers are extremely large. C to the power d it becomes large even for this simple example. So for this reason, RSA is computationally quite expensive. Public key encryption schemes are in general more computationally expensive than symmetric key encryption schemes. Now recall that the encrypted value C is m to the power e mod n. The value obtained after decryption is performed by Bob is m prime equals c to the power d mod n. Now let's substitute for C from this equation into this equation. So we get m prime equals m to the power e mod n, the whole to the power d mod n. By the properties of modular arithmetic that we discussed earlier, this is the same as m to the power ed mod n. Now the claim is that m to the power ed mod n is equal to m. So if we prove this claim, then that will prove that the value after decryption is the same as the original plain text. We have to prove that e to the power ed mod n is m. So we now study some basic results from number theory, and we'll then later use these results to prove this result. So we require the following results from number theory. One is Fermat's little theorem. Let p be a prime number. If a is a positive integer, then the claim is that a to the power p mod p is equal to a mod p. Here's an example. Let p be 5 and a be 8. Then it can be checked that 8 power 5 is 32768. So 8 to the power p mod p is 3, and that is the same as a mod p, which is also 3. So 8 mod 5 is 3. So this theorem is verified for this example. Let's prove this theorem in general. First, we expand a to the power p mod p using the multinomial theorem. So we write a as 1 plus 1 plus 1 and so on. There are a terms in this sum. So we write a as 1 plus 1 plus 1 and so on, and then use the multinomial theorem to expand a to the power p. So a to the power p mod p can be written as 1 plus 1 plus 1 and so on to the power p mod p. Now recall the multinomial theorem, which is a generalization of the binomial theorem. It allows us to write an expansion for this quantity. So if we expand this using the multinomial theorem, we get a terms which are all 1 to the power p, that is the same as 1, and then we get some other terms mod p. Now each of these other terms is of this form: p factorial divided by r1 factorial, r2 factorial up to ra factorial, where r1 to ra belong to the range 0 to p minus 1, and r1 plus up to ra equal to p. This is the multinomial coefficient. Notice that it's a generalization of the binomial coefficient, which is n choose k. So if we expand this using the multinomial theorem, we get such an expansion. Now since p is a prime number, the factor p in the numerator here does not cancel with any of the terms in the denominator. So there is a factor p present in this multinomial coefficient. So each of these other terms has a factor p in it. So when we take mod p, all these other terms vanish. After taking other terms mod p, all the other terms mod p are equal to 0. So hence the result is just the first a terms survive, and the result is a mod p. So that concludes the proof of this theorem, that a to the power p mod p equals a mod p. Another result from number theory that we require is Bezout's identity. This is also known as GCD theorem. We discussed this result earlier. Recall that if a and b are integers with GCD d, then there exists integers x and y such that ax plus by equals d. For example, if a is 5 and b is 8, then such numbers x and y are x equals minus 3 and y equals 2. So we can check that ax plus by equals the GCD of 5 and 8, that is equal to 1. So we recall these results from the previous slide. Now a corollary of these results is that if p is a prime number and if a is a positive integer that is not divisible by p, then the claim is that a to the power p minus 1 mod p equals 1. So we'll require this corollary to prove the correctness of RSA. let's prove this corollary. By Bezout's identity, there exists integers x and y such that a to the power p x plus p y equals the GCD of a to the power p and p, that is equal to 1. The GCD is 1 because p is a prime number. So, hence clearly a to the power p and p are relatively prime. So, there exists such integers x and y. Now, we are interested in a to the power p minus 1 mod p. So, let us try taking mod p throughout this equation. So, taking mod p throughout this equation, we see that py mod p is 0. So, hence we get from here a to the power px mod p equals 1. But a to the power px mod p can be written as a to the power p mod p times x mod p the whole mod p by the properties of modulo arithmetic that we discussed earlier. But by Fermat's little theorem, a to the power p mod p equals a mod p. So, hence we get this a mod p times x mod p the whole mod p, but that is the same as ax mod p by Fermat's. So, we have used Fermat's little theorem in this step while going from year to year, and hence we get that a to the power px mod p equals ax mod p. So, in this step we have shown that a to the power px mod p is 1. So, hence from this step it follows that ax mod p equals 1. Now, consider again a to the power px mod p. It can be written as a to the power p minus 1 mod p times ax mod p the whole mod p. So, we have already shown that ax mod p equals 1. So, hence this LHS becomes equal to a to the power p minus 1 mod p. So, the result follows from 1 and 2. So, in 1 we have shown that a to the power px mod p equals 1. So, hence the LHS is 1 in this equation. So, hence a to the power p minus 1 mod p equals 1, which is what we wanted to show. Now, again recall the Chinese remainder theorem, which is another result that we discussed in the mathematical background for cryptography. If p and q are relatively prime, then this set of equations x mod p equals a and x mod q equals b has a unique solution for x modulo pq. So, we discussed the general form of the Chinese remainder theorem, where we have multiple factors. We have k factors, say p1, p2 up to pk. Here we only require the special case of two factors p and q. So, for the case of two factors, this is the form of the Chinese remainder theorem. Now, we return to the proof of correctness of RSA. Recall this theorem, m to the power ed mod n is m. So, we will prove that m to the power ed mod p equals m mod p, and we will also prove that m to the power ed mod q equals m mod q. So, once we prove one of them, the other follows by symmetry. So, then the claim is that this result will follow from once we have proved these properties. This result follows from the Chinese remainder theorem. The reason is that p and q are relatively prime. Since they are prime, they are clearly relatively prime. And m to the power ed mod p equals m mod p, let us call that a. And m to the power ed mod q equals m mod q, let us call that b. This is a system of equations of the form x mod p equals a and x mod p equals b. So, this equation is of the form x mod p equals a and x mod q equals b. But this is exactly the form of equations that appear in the Chinese remainder theorem. So, we know that this system of equations has a unique solution modulo n, that is modulo pq. But clearly, trivially, m is itself a solution of this system of equations, because m mod p is a, which is m mod p, and m mod q is b, which is m mod q. So, m is a solution of these equations. But once we have proved that m to the power ed mod p is a and m to the power ed mod q is b, then it will follow that m to the power ed mod n is the same as m. So, m to the power ed mod n is m. That will follow from these properties. So, this result holds by the Chinese remainder theorem. Now, we recall that ED is 1 plus kz for some positive integer k, where z is p minus 1 times q minus 1. This is true because ED mod z is 1. So we can now substitute for ED from here. So this becomes m to the power 1 plus k p minus 1 times q minus 1 mod p. And we have to show that this is equal to m mod p. Now consider this LHS. This is equal to m mod p times m to the power k p minus 1 q minus 1 mod p, the whole mod p. But by the above corollary to Fermat's little theorem and Bezout's identity, we know that m to the power p minus 1 mod p is 1. So hence this LHS is the same as m mod p. So hence this is the same as m mod p, which is what we had to prove, and then the result follows from the Chinese remainder theorem. So this proves that this proves the correctness of RSA, that the value obtained after encrypting the plain text and then decrypting the ciphertext is indeed the original plain text. Now we discuss the reason why E and Z have to be relatively prime. Recall that Z is p minus 1 times q minus 1, and E is less than n is chosen such that E and Z are relatively prime. So the reason is that if E and Z are relatively prime, then there exists a positive integer d such that ED mod Z is 1, and we require this positive integer d for decryption. So the proof is the following. By Bezout's identity, there exist integers x and y such that Ex plus Zy is equal to the GCD of E and Z, that is equal to 1. Taking mod Z throughout this equation, we get Ex mod Z is 1. But since x may be negative, let d be x plus kz, where k is a sufficiently large positive integer. It's sufficiently large so that d becomes positive. Now d mod z is equal to x mod z. Further, if we substitute d into this equation, then we get that ed mod z is ex mod z plus 0. We get that ed mod z is 1. So hence there exists a number d such that ed mod z is 1. That's what we have shown. Now d can be efficiently computed using the extended Euclidean algorithm, which we discussed during the mathematical background of cryptography. So recall that for given integers a and b, the extended Euclidean algorithm finds the GCD of a and b as well as integers x and y such that ax plus by equals GCD a comma b. Now, why is RSA secure? Recall that the public key is the pair n comma e and the private key is the pair n comma d. So n and e are publicly known. So if an intruder could factor n into p and q, then the intruder knows p and q. Then from p and q, the intruder can calculate z equals p minus 1 times q minus 1. And once z is known, then the intruder could find out d using the extended Euclidean algorithm. But the problem is that there is no efficient algorithm known for factoring a number n into its prime factors p and q. So if such an efficient algorithm were found, then RSA would be broken. But on the other hand, it has not been proven that no efficient algorithm exists. So since there is no efficient algorithm known for factoring a number n into its prime factors p and q, on this fact the security of RSA rests. So even though n is a part of the public key, it is computationally infeasible to find out p and q from n, and hence it's computationally infeasible to get the private key. Also, no efficient algorithm is known for finding d directly using n comma e. So for these reasons, RSA is secure. Now recall that if the plaintext is m, then the ciphertext is c equals m to the power e mod n. If m and or e are small, then it is possible that m to the power e is less than n. So hence m to the power e mod n is the same as m to the power e. So the intruder could decrypt the message by just finding the eth root of the ciphertext. So by taking just the eth root of m to the power e, the intruder can get back the plaintext m. So decryption is so breaking the cipher is quite easy. So such problems can be avoided by padding each message m by some bits before encryption. So m is padded with some bits so that it becomes large enough so that m to the power e becomes greater than n. So by just merely taking the eth root, the intruder cannot get back the plain text message m. Now we showed that kb minus of kb plus of m equals m. That is, by first applying the public key to a plain text message m and then applying the private key, we get back the original message m. And a simple exercise is to show that if we reverse the order of operations, that is, first we apply the private key kb minus to m and then apply the public key to the result kb plus of kb minus of m is the same as m. So in this case, in this exercise, we first start with a message, say c, and then we perform, we find out c to the power d mod n. Let's call this say x, and the claim is that x to the power e mod n is the same as c. So that's what this says. So if we first use the private key and then we use the public key, then we get back the original plain text message m. So later we'll use this fact to design digital signatures. Now encryption and decryption using DES or other symmetric key ciphers is at least 100 times faster in software and between 1,000 and 10,000 times faster in hardware than RSA. So this is the general trend that symmetric key algorithms are much more computationally efficient than public key algorithms. So now suppose a large file needs to be transferred from Alice to Bob. Alice and Bob do not have a shared key available in advance. So one way to securely send the file is to encrypt the entire message using RSA. But this is very slow because as this shows, encryption decryption using RSA is very slow. So can we somehow combine DES and RSA to send the file securely faster? So this can be done as follows. Alice first selects a string KS randomly and then encrypts it with RSA to Bob. So Alice selects a random key KS and then encrypts it with RSA and then sends it to Bob. Then the large file is sent after encryption using DES with KS as the shared key. So once KS has been securely sent to Bob using RSA, now Alice and Bob have agreed upon the secret symmetric key KS. Subsequently, they can use a symmetric key algorithm like DES to send a file itself using symmetric key encryption. So in this way, we can combine public key encryption with symmetric key encryption to encrypt a file and send it very fast. So we just mentioned DES and RSA as examples, but we can combine any public key algorithm and any symmetric key algorithm using this procedure, and using the combination we can send a file faster. This concludes our discussion of RSA. Thank you.